Atoms are packed with positively charged protons that constantly push each other away with massive electrical force. So why don't they just fly apart? Let's look at how neutrons hold protons together, and why too few or too many of them can collapse the atom. The main thing is that protons and neutrons can transform into one another, but only if they have enough energy. This process is called beta decay. A free neutron has just enough energy to decay into a proton in about 15 minutes. But a proton always has less energy and cannot freely transform into a neutron. Yet if we put two protons close enough, their combined energy will be high enough to flip one of them into a neutron. And on the other hand, two neutrons always have the energy to turn one into a proton. This makes a proton-neutron pair the most stable setup of these two particles. The particles get locked in their current state since every other system has more energy and eventually transforms into this one. And if previously the neutron had enough energy to transform, now some of the energy of particles converts into the binding energy, which locks them together. That's why neutrons bound within atoms remain stable, even though they decay in minutes on their own. This ratio of one neutron to one proton is valid for most elements consisting of fewer than 40 particles. But in larger atoms, the situation gets different. Though the force that holds neutrons and protons together is usually stronger than the electrical repulsion, it acts over extremely small distances, binding only the nearest particles. Meanwhile, unlike the short-range nuclear force, electrical repulsion of protons reaches across the entire nucleus. As a result, each added proton experiences repulsion from all protons in the nucleus, while it is held only by its nearest neighbors. However, the electric force still weakens as particles move apart. So, when adding a few neutrons to the atom, the protons move further apart and their repulsion gets weakened, while total attraction becomes even stronger. We can keep adding neutrons until their total energy gets high enough to turn one of them into a proton. And on the other hand, if there are too few neutrons, some protons can transform into neutrons to increase stability. This principle gradually shifts the balance to the ratio of 3 neutrons to 2 protons in the heaviest stable elements such as lead. But in even heavier elements, the number of protons gets so high that the nuclear force can no longer counteract the repulsion of a new proton. Even though this proton could potentially turn into a neutron to get rid of the repulsion, this would result in a large increase in the total energy of neutrons. Eventually, the nucleus gets so saturated with energy that it starts spitting out particles to restore balance. This leads to alpha decay, where an alpha particle consisting of 2 protons and 2 neutrons gets emitted from the atom. This particular particle is so common because it has the perfect nuclear ratio. It's easier for the nucleus to eject a whole alpha particle at once rather than all 4 particles one by one. In this way, neutrons balance powerful energy of protons, while nuclear decays are simply ways of restoring the particle balance in the atom.